Hassler here. I'm going to be giving these 3.8 notes on inverse functions in class, but I am recording these just in case somebody is absent or just in case you decide that you would like to go back through a couple of the problems. So I'm just going to be linking this as a YouTube link. This is not required to watch. All right, so I just want to recall what an inverse function is. So an inverse function is 1-to-1, and 1-to-1 means that if I were to graph a function that has an inverse, it means that that function would pass both the vertical line test and the horizontal line test. So for example, if I were to look at the graph of a line, and I were to draw a vertical line that would pass through any point on this line, so that means it's a function. But if I were to draw a horizontal line, it would only pass through one point at a time on my blue line, meaning that I could find an inverse of this function, and the inverse of this function would also be a function. That does not hold true if I were looking at a parabola. So a parabola passes the vertical line test, meaning when I draw that vertical line, I only pass through one point at a time on the parabola. However, when I draw a horizontal line, I'm passing through 2 points at a time. In other words, there is not an inverse function for a parabola. And so in order to create an inverse for parabolas or quadratic functions, we have domain restrictions, okay? So an inverse function in its natural state passes both the vertical line test and the horizontal line test, or if it does not pass the horizontal line test in its natural state, then we often put domain restrictions. A domain restriction in this particular case would mean that we say, well, I'm going to look at the parabola for x values greater than 0. If I look at the parabola for x values greater than 0, I would pass the horizontal line test. Therefore, that part of the parabola would have an inverse function. Okay. Look at this composite. We say f of g of x is equal to x for every x in the domain of g, or g of f of x is equal to x for every x in the domain of f. And all that is saying is that I'm going to lighten this up a little bit. All that is saying is that inverse functions undo each other, okay? It's like saying that I'm going to take 5, I'm going to multiply x by 5, and then I'm going to go and divide x by 5, and I'm left with x. So multiplication and division are inverses of each other. If I were to take the number 5 and the square root of that, and then I were to square that number, I would get 5 back out. That's what that's saying, okay? That square rooting and squaring a number, those two operations undo each other, okay? All right, some properties of inverse functions. Given f of x, then the inverse function is written as f inverse of x, and so that -1 is the notation to indicate that you have an inverse function. The graph of the inverse is a reflection of f over the line y equals x. Okay, so going back up to my graphs here, if I were to draw in the line y equals x, then the reflection of that over that line, that would be my inverse function, okay? If the point xy is on the graph of f, then the point yx is on the graph of the inverse, okay? Is on the graph of g. I know I write g here, but oftentimes we say, well, g is the inverse of f. So that's what this is saying, is that if xy is on f, then yx is on the inverse of f. I switch the ordered pairs when looking at inverse functions, okay? Let's look at derivatives of the inverse. So assume that f is differentiable. I can find the derivative of f and is 1-to-1, meaning that it passes both the vertical line test and the horizontal line test. We're going to call the g function the f inverse function. If b, some given x value, is in the domain of g and f prime of g of b is not 0, I'll remind you of that in a second. Then the derivative of g, the derivative of the inverse, g is the inverse, exists and is given by g prime of b equal to 1 over f prime of g of b. And I'm just going to write this in a slightly different way. I know it can be a little confusing that I called f inverse g. I was just trying to clean up the notation a little bit, but to help lessen the confusion, this is the same as saying that f inverse prime of b, okay, is equal to 1 over f prime of f inverse of b, okay? Okay, something you have to memorize, all right? And so I'm going to go through some examples. Again, this is what I do in class. This is not anything new or extra you're required to watch, but perhaps you would feel like rewatching it would be beneficial because magic happens in class where I talk too fast, and I totally get that. Okay, so we're going to talk through some of these. It says let g of x be the inverse of f, right? Again, all that means is that g of x is f inverse of x, okay? The selected values of f of x and f prime of x are given in the table below. Which of the following is the value of g prime of 3? Another way to ask that is what is the following of f inverse, I want to erase that because it looks too close, okay? What is the derivative of f inverse of 3? That's the other way to write it, okay? So in other words, I want to find the derivative of the inverse function at 3. Whew, okay. Here's what I know. I know that if I want to find this derivative, however you want to write it, either with g's or with f inverse, I have to fill out this formula. I have to fill out 1 over f prime of g of 3, okay? Again, another way to write that, if that g is confusing to you, f inverse prime of 3, I have to fill out 1 over f prime of f inverse of 3, okay? So whatever way you want to go about it, these two things mean the same thing, all right? I just know that oftentimes the AP problems like to call f inverse g, and so I'm just trying to expose you to that notation and that representation. I also want to expose you to both ideas in case your brain works better one way versus the other. What this means is that I first have to evaluate f inverse of 3 or g of 3, where g is the inverse of f. And what I like to do is I like to write out what's going on with these ordered pairs, okay? In other words, if I have the f function and I know the ordered pair for that f function, then I could just switch those ordered pairs in order to figure out what's going on with the g function, okay? So the first part of this derivative formula is that I have to evaluate the inverse at 3. In other words, I have to evaluate what's happening here. My goal is to figure out what the output is when I put 3 into the inverse function. Right, I got to evaluate g of 3 or f inverse of 3. The problem is that my table is not written in terms of f inverse or in terms of g's. But I do know that inverse functions flip their ordered pairs. And so if 3 is the input for the inverse function, that means that 3 is the output for the original function. Okay, that's one of the properties of inverse functions. If 3 is the input for the inverse function, 3 is the output for the original function. So what I'm going to do is I'm going to look at my table and I'm going to say, okay, for the f function, I need an output of 3. And the input that goes with that is 1. Okay, so when I do f of 1, I get 3. The inverse function flips those. 1 is what I was looking for, okay? So g of 3 is 1. I now get to evaluate f prime of 1. Same thing down here. F inverse of 3 is 1. Either way, I have to evaluate f prime of 1. All right, so f prime of 1 is 5. My derivative of the inverse function at 3 would be 1 over 5. And I'm telling you guys, I really think that this is the ticket right here, okay? This is the big idea, is this idea that my ordered pairs flip for an inverse function. And if you can organize yourself in that way and you can keep track of this derivative function, you should be good to go. All right, I'm going to do the second problem on this front side. It says, let g of x be the inverse of f. Okay, same directions as above. Given the following values on the table below, at which value x equals a, will the derivative of the inverse be 1/6? So this time I'm telling you the answer. Okay? Again, let's set up this derivative. So that means that g prime of a, because I don't know what a is going to be 1 over f prime, so the derivative of the original function, of g of a. And if you'd prefer, we can say f inverse prime of a, right? The derivative of the inverse at a would be 1 over f prime of the inverse at a. And I know that this is equal to 1/6. So I know the answer this time, okay? All right, so I know based on this setup that f prime of g of a equals 6, or you could say f prime of the inverse of a, the inverse of f at a is 6. And so that's the equation that I'm trying to solve, okay? I'm trying to solve f prime of g of a is equal to 6, okay? Okay, so I am looking for, in my table, I am looking for where f prime of what equals 6. Okay, so f prime of, okay, the output for f prime is 6, and that happens when the input is 2. I know, wrong thing. I know that f prime of 2 equals 6, okay? That's what the table tells me. What that means is that g of a must be equal to 2. So now my job is to figure out when g of a, which again, by the way, is just f inverse of a is equal to 2. My apologies. Right, that's what this says. If f prime of 2 equals 6, then that means that the g of a, or f inverse of a, has to be equal to 2. I've got to figure out when that is going to be equal to 2. And again, I'm going to go back to this ordered pair idea. Okay, so again, f inverse, which is the same as g. All right, this tells me that the output, this right here tells me that the output of the g function is 2. So this time I'm going to put the 2 in the output spot. And if 2 is in the output spot for the g function, then it's in the input spot for the f function. Okay, so f of 2 is 5, which means that if I flip those for the inverse function, the ordered pair for the inverse function is 5, 2. What that means is that g of 5 equals 2. That must mean that the a value is 5. Whew. All right, I know, in your brain, it's like a puzzle, and your brain goes to mush in the middle of it, right? So the big idea here was this. The big idea was that I recalled what the derivative of the inverse function is. I noticed that I have to figure out when the derivative's denominator is equal to 6. Okay, and I looked at my table and I said, okay, well, f prime of 2 gives me 6. The 2 then has to be related to the g of a, or the f inverse of a. Okay, if I do f prime of 2, that gives me 6. That means I have to figure out when g of a, or f inverse of a, is 2. That's what I did here. I use the ordered pairs to help me do that, keeping in mind that ordered pairs flip when it comes to inverse functions. I use that idea to help me figure what the a value should be. Okay, so I can go back and check this. Okay, I can go back and check this and say, listen, if I go back and check this, I would write g prime of 5. That's what we said a was, right? G prime of 5 would be 1 over f prime of g of 5. And again, you could use this with the f inverse. F inverse prime of 5 would be 1 over f prime of f inverse of 5. Okay, so again, just a reminder, if I'm saying that f inverse, which is g, the input is 5, that means I'm looking in my table for when the output is 5 at f. Okay, the output is 5 when x is 2. Oops, duh. And so that means that if the input is 2 for f, that's the output for the inverse. So g of 5 would be 2. So I'm doing 1 over f prime of 2. And f prime of 2 is 6. And I get that 1/6 that they were asking about. This was just me checking to verify that the a value is truly 5. Okay, so again, we're doing this in class. I am going to go ahead then and let people in class work through 3, 4, and 5. And so if you are absent, then I would try 3, 4, and 5 and come in the next day or live stream with me so that we can go over those answers. Thanks.